Okay, now we can actually start doing our calculations. So let's start with 1. We want to show that u and v are characterized by the above ordinary differential equations. Now, how do we show that the derivative of u is something? Well, one good way would be differentiate u with respect to t. So let's try that. I have the definition of u of t from the book over here. So if I try to just write d to t u of t is equal to d to t of this integral here, well, then what happens? Well, first of all, there's something not so nice about having a t inside the integrand and a t in the boundary. I actually know what I can do about the t in the boundary, because for that we can use the fundamental theorem of calculus. What does the fundamental theorem of calculus tell us? Well, the fundamental theorem of calculus tells us about the relation there is between a function's derivative and between the derivative and the antiderivative. So what the fundamental theorem of calculus tells us is if I have a function f and I integrate that with respect to its argument up to some point t, regardless of what's in the boundary down here, it can be any a, then I actually have that this integral is equal to that. If I take this integral and I want to differentiate it with respect to t, then this integral is equal to f of t. And that is the fundamental theorem of calculus. It tells us the antiderivative. If you take the derivative of the antiderivative, then you get the function itself. So the fundamental theorem of calculus. And we can use it here. The only problem is, well, I also have a t inside my integral, but we can figure that out. Now, how do we do that? Well, the thing I do now is I take the e to the delta t outside of my integral. I can do that because nothing here depends on s. And now I have e to the delta t multiplied by an integral that looks like this. Okay, what I use now is the product rule of differentiation. If you can't remember it, go on the internet, Google it, and come back. So the product rule tells us that the derivative of the product of two functions is equal to the derivative of one multiplied by the other function and the derivative of the other function multiplied by the first function. So let's try to take a look at this. I will leave e to the delta t undifferentiated first, and here I have the derivative of the integral, which according to the fundamental theorem of calculus, then is just e to the minus delta t multiplied by c of t minus b of t, like that. And then the second term using the product rule is the first part differentiated, which, well, it's not that different. I just get a delta down here, e to the delta t, and then the second part non-differentiated. So integral 0 to t, e to the minus delta s, c of s minus b of s ds. Great. Okay, so plus fundamental theorem of calculus. Okay, what do I have now? Well, e to the delta t and e to the minus delta t kind of cancel. So I have c of t minus b of t. And then I noticed that if I consider this thing here, then it's actually exactly the same as u of t. So that's just plus delta u of t. Just look at this and look at what's above if you're not completely convinced, and then you will be convinced. So this thing here is just equal to u of t. And that was the first part of what we needed to show up here. And also we need to show that u of 0 is equal to 0. And that's quite easily seen by the fact that u of 0 is equal to this integral with 0 in the upper bound, so it's integral from 0 to 0. And then no matter what's in here, when we integrate that with respect to s, that's just equal to 0. So check, that's done. Now we want to show that the second differential equation also holds. And we'll go through that one just a little bit quicker. So I have derivative of v with respect to t. That is, well, let's see, d to t, and then I have the integral from t to n e to the minus delta s. And already now I will take the e to the delta t outside of the integral, like this. And then I have b of s minus c of s ds. And I can use the product rule yet again. So product rule and fundamental theorem of calculus. So I have e to the delta t not differentiated, and then I derive this integral with respect to t. Now, a funny thing kind of happens here because the fundamental theorem of calculus needs the t to be in the upper bound here. And how do I do that? Well, there is an integral rule that says if I have an integral that goes from, well, for example, from t to u, blah, 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 then that is equal to minus the same integral from u to t. So I can use that rule here. And then what I get is just the innards, but with a minus sign. So I have a minus sign and e to the minus delta s multiplied by b of s minus, e to the minus delta t multiplied by b of t minus c of t. And then the last part, it's just the calculations go exactly as they did in the first one, so we will be left with delta v of t. Okay, just check this calculation if you're not sure, but I'm sure. So what do we see here? The e to the delta t and e to the minus delta t go out, and we're left with delta v of t minus b of t with the parentheses on, minus c of t here. And that was also the result we were supposed to show. Now, for v of n equals 0, well, again, we note that if I plug in n t's place here, then I just get the integral from n to n. And no matter what the innards are here, it's just equal to 0. So that one is also done. Now, the next video will focus on part 2 and 3. I won't do that here because this video is already getting a bit long. But for that, we will need a bit of proof technique. So look forward to it.